Yes. So I'm happy to introduce Beatriz Soret, who is joining us from Aalborg University. And she will be talking to us about non-terrestrial networks in beyond 5G communication systems. And the speaker has a lot of experience in the area of wireless communication. She received her master's and PhD in telecommunications from Universidad de Malaga in Spain. And then she's currently an associate professor at Aalborg. She was with Nokia Bell Labs and GOM Space. She has co-authored more than 70 publications and has a Best Paper Award from IEEE Globecom 2013. She holds 16 patents in the area of wireless communications. Her research interests are with satellite communications, with low Earth orbit constellations, low latency communications, and age of information, IoT connectivity, as well as 5G and post-5G systems. So please join me in welcoming Beatriz.
Yes, so thank you very much for the introduction. Yes, so hello everybody. As Elif was saying, I'm an associate professor in wireless communications in Aalborg University in Denmark, and it's a pleasure to be here today and to tell you a little bit about some of our research, which is about satellite communications in 5G, beyond 5G and 6G networks. So I hope you'll find the topic interesting, so feel free to interrupt me if you have questions during the presentation. This is the outline. So I will first tell you a little bit about non-terrestrial network and the standardization process that it's ongoing. And then I will focus on the LEO, the low orbit satellite constellations. And I will give you an overview of 3 research programs that we are working on related to these huge constellations. Okay, so where are we? It's now more than 50 years since we had the first man walking on the moon. And after these golden years, there was a period in which there was a little bit less interest and less investment on space technologies and satellite communications. But now we are in a very different situation. So it's now several years that there has been a lot of hype actually around space technologies and satellite communications. And there is more and more investment and interest, not only from the industry, but from the governments as well. And actually you have here a number that by 2025, it's expected to be like $7 billion of investment in this area. And there are several reasons for this very good moment for satellite and space. So in the old space, so the initial space years, what we had is a situation with very expensive rockets and very expensive satellite technology and long deployment time. So it was a slow technology. It took many years from the moment in which you decide that you want to start a project until you had the technology up and running for you. Due to the price, this old space was in the hands of a few rich countries and at the government level, so at the country level. The new space, which is what we have now, it has very different rules actually. One of the big drivers is this miniaturization of the satellites. So now we have this paradigm, which is called the CubeSat, you have in the picture here. It's a small satellite of 10 by 10 by 10 centimeters. And this is the minimum unit that you can have up and running. So this is a fully functional satellite, of course, with a limited capacity. So it's not that you can do everything with this small unit, but you have a fully functional satellite. So they can be really small. You can also, if you need extra functionality, you can pile up several of these, and then you add extra computation and communication capabilities. But in general, what we call the small satellites, they are a few kilograms. They are also very cheap because they use commercial components, and also because when you have to launch them, because they are a few kilograms, you can just use a rocket that is launching a big satellite, and then just put your small satellites as a secondary payload. And this will dramatically reduce actually the cost of your space mission. So this is actually a very important reduction in the cost for this technology. And also the development times, they are much shorter. So your technology does not become obsolete in the meantime. So this is one of the drivers. And then we also have the privatization of this area. So now it's not only the governments, but there are more and more big companies, but also small companies, because they can just maybe launch one of these small satellites, and it's still not too expensive as it used to be. And at the same time, we are in a moment of a lot of new applications related to the IoT domain, but also related to Earth observation and other services. So there are a lot of new services, and some of them are, it makes sense to support them with a satellite technology. So these three reasons, they are like the perfect context to have this increased interest in space technology right now. All right, so this is where we are. And then we have 3GPP. 3GPP is a consortium of the big mobile companies, and they are responsible of standardizing many of our communication systems, including 4G, 5G, the future 6G. So they have to agree on what's exactly what has to be in the standard to be sure that then the mobiles, they can talk to each other, no? For example. So this is a 3GPP. When they saw the big interest in space technologies in 2018, they decided that they also wanted to get part of this cake. So they decided to standardize satellite communications and to integrate them with 5G networks and beyond 5G and 6G when we get there. So 3GPP started some work in the standardization process, and they call it non-terrestrial networks, and they use this NTN, and it's about the integration of terrestrial networks and satellite communications. In the figure, you can see that it's not only satellite what they consider here, but they also have these airborne vehicles. Like, for example, you have these balloons or these high altitude platforms and drones. So they are all part of this non-terrestrial network acronym in 3GPP. It's true that in this initial phase, most of the work is on the satellite. I have not seen anything specific about the airborne vehicles yet. They have separated work items for the drones, but the hybrid architectures and the integration, I think it will come a little bit later, but it's in principle, it will be part of it as well. In the standardization process, the plan is that they should have something by the end of next year, but with the COVID, everything has been postponed a little bit. So they have some delays because they had to change the way they work, no? Because they used to travel a lot, now they have to do everything remotely. So there are some delays and some impact of the COVID on the standardization process. Yeah, and also some prioritization. So let's see, maybe it will be a bit later than expected, but it will be there. Regarding the kind of applications for satellite, you have in this figure a lot of different applications. So we have the traditional satellite applications, like for example, for Earth observation or for tracking airplanes. But we also have some new applications or applications that used to be more for terrestrial networks, like broadband connectivity, for example. One of the advantages of satellite is ubiquity, meaning that you can reach remote areas that it's not possible with a terrestrial network, or it's too expensive with a terrestrial network. So, for example, the oceans, the oceans, they are not covered with terrestrial networks. This is where we put a satellite, and it makes a lot of sense. And also, I don't know, in the middle of a mountain, maybe you could deploy a base station, but it's too expensive. So it's easier to use satellite connectivity. So this is what you see in the right part of the slide. The remote areas and the rural areas, they have a lot of applications that are important there, but also in an urban area where you have typically a good terrestrial network. The role of the satellite here is then to complement this terrestrial network. For example, if you have some areas that are very congested, you could offload part of this traffic to the satellite segment. Or if you have some outages at some point, you can get the support from the satellite to be sure that the service that you provide is continuous and is not disrupted. So this is some of the examples of applications. Regarding orbits, the initial space technology, satellite technology was on the geostationary orbit. This orbit is at 36,000 kilometers. And the reason for it is that this way, the satellite is moving with us at the same speed. So it moves with the Earth rotation, meaning that the orbital period is 24 hours. It takes exactly one full Earth rotation to reach the same position again. So the initial satellites, they were deployed at this height. This means that for us, imagine for me here in Denmark, the satellite that I have covering my area, I see it always in the same position. So it's fixed to me because we are moving all together. The problem of these geo orbits is that the height is very large, so the propagation delay is very large. It's already more than 100 milliseconds. This is due to the large distance between me and the satellite. And there is nothing I can do about this. There is nothing I can optimize here because this is physics, right? So for sure, my total latency in my communication is at least more than 100 milliseconds. This is not enough for many communication applications. So the trend is to go lower and lower in the orbit to support also these delay-sensitive applications. So you find them, these LEO and these MEO orbits, and the interest is right now on the LEO, so going lower and lower. Low Earth orbit, they go between 300 and 1,500 kilometers. And if you look at the propagation delay, now it goes down to a few milliseconds. This means that now you can support a lot of applications that are kind of sensitive to the delay. The problem of going lower in orbit is that now the satellite is not in a fixed position. So now a satellite pass, it's only a few minutes. So I see the satellite, he's passing, and after a few minutes, it will disappear on my horizon. So if I want to have some continuous service and global service, I have to deploy many of these satellites. So when one disappears, I will have the next one coming right after him to cover my area. So from an engineering point of view, it's a lot of added complexity, but this is the price to pay to have new applications with reduced latency. And this is what we are doing. You also have in the slide in the lower part the frequencies that are proposed for these communications. So they go from the 1 gigahertz to the Ka band at 40 gigahertz. All right, in terms of requirements for the communication network, there is this document from 3GPP where they have the requirements for 5G. If we take a look at these examples of requirements, for example, the first one, the reliability. So the reliability for a terrestrial network is defined as the probability that a data of size D is successful transfer within a time period T. And for 5G, there was this service that they call URLLC, in which it was decided that this reliability should be 10 to the minus 5 for a small packet of only 32 bytes within a latency of 1 millisecond. Okay, so it means that they have to be successful in at most 1 millisecond. The first observation here is that if I have a satellite link, this is impossible, because even if I have a very low orbit, my propagation delay is already few milliseconds. So there is no way I can fulfill this requirement. But so far, there have been no updates here. So in principle, this service is not supported with a satellite link. For the latency instead, that they define like the round trip time, we can see in the document that they have already updated it to include satellite communications and to include the fact that the propagation delays, they have an impact here that we cannot really optimize. And you can see that, for example, if you have a GEO, so at 36,000 kilometers, the latency now can be up to 600 milliseconds. So this way we can support this kind of services with a satellite network. It's true that there are also more and more services that actually they are not really sensitive to this latency or the packet delay, as 3GPP is defining it. But actually now there are new metrics that can be more interesting for many applications. Because imagine, for example, when you have a tracking application, the receiver is not really sensitive to the packet delay, but it's more interested in the freshness of the information at the receiver. And I will give you an example here. For satellite, we have this application, which is satellite tracking. I don't know if you know this website, this Flight Radar 24, but it's basically the current picture of all the airplanes on the Earth. So each yellow dot its yellow airplane is the current position. And the way this system works is that the airplane is periodically sending messages, is broadcasting, so to everybody that is around, telling, okay, this is me, this is my current position, and I'm flying in this direction. So it's status information. And every time t, this status is transmitted again with the new coordinates. All right, and the terrestrial part is covered by terrestrial networks, but in the oceans, this is supported by a satellite network. In this kind of applications, the monitor, so the one that is plotting this figure here, is not really interested in the single or the individual delay of one of these status reports. No, what is important here is that the yellow airplane that I'm plotting here is representative of the current position of the plane, no? That I'm not too wrong and I'm not too, plotting a very wrong position here. So this is why we say that many applications are more sensitive to the freshness of the information at the receiver. In terms of architectures, we have here 3 examples of how to use a satellite with a terrestrial network. In the first one, this is the simplest case in which your satellite is used as a relay, as a communication relay. What we have here is, I should have my pointer. No. Okay, no, not working. Well, okay, in the upper part of the slide with a relay, what we have is the UE, for example, the mobile, wants to connect to the base station, which is the G node B in 5G notation. And this will then go to the internet, to the core network of the operator, and then finally to the internet. No? But if we look at the left part, what we have here is that instead of connecting directly the UE to the G node B, we use a satellite because maybe the G node B is too far, is not reachable, or for any other reason. But this relay here is a very simple relay that will just take the signal, amplify, and forward again, without any complex processing or decoding or anything else. So it's a very basic functionality. Okay, so it's you can say a very stupid satellite in this case. The second case is more complex, and the satellite is now taking the role of a full base station. So it's 5G G node B. The only difference is that it's flying instead of the terrestrial base station. So the satellite will get the signal from the UE, will do all the processing, and will send it to the core network of the operator, and this will then go to the internet, to the data network. So this is a more complex functionality on the satellite. So you need more capabilities on the satellite to support this case. The third use of a satellite is as a backhaul. So the backhaul is the link that connects your radio access network, where you have the base stations. So it's the part that is close to the UE. It connects this to the core network of the operator. And typically this backhaul, in terrestrial networks, it's a fiber, or it's a very good optical link. But it was not a good option to have a satellite link because it was too expensive, basically. But now there are more and more situations in which it makes sense to have a satellite that is giving you this backhaul capability. And this is what you have in the figure. You can see that now the satellite is between the radio access network, so the base stations, and the core network. All right, and now I want to tell you a little bit more about these LEO satellite constellations. You probably have seen or have heard about them because they are very often in the news, no? And there are some commercial examples that are, they have very strong marketing campaigns actually. Like for example, the project from Elon Musk, Starlink, you probably heard of it. These constellations, it's basically, it's a lot of satellites that they are organized in several orbital planes, and they work all together as a single communication network. As I said in the beginning, no? If you have a very low orbit, you need to deploy a lot of satellites to provide continuous coverage. So this is why we have these very dense constellations. And you have different topologies, and in general, you need at least hundreds of satellites, but some of them are even thousands of satellites to have a very good coverage and very good performance. They have a lot of similar things with terrestrial networks, and in general, we should try to use all the knowledge that we have from terrestrial networks and adapt it to satellite. But there are also new challenges that we have to consider. The first one is obvious with LEO orbits, is that the infrastructure is now moving. When we have a terrestrial base station is fixed, I can always go there and fix something when it's not working. For example, this is something I cannot do with a satellite because I cannot reach it once I have launched it. And the fact that it's moving, it has some additional challenges. I will have some Doppler effect, and also the contact time. So the time that the link is available, it changes, no? The second difference is the propagation delay, as I mentioned. No? There are some physical limits that I cannot do anything about them. So this is important to take into account in our designs. And then in general, I want to use small satellite technology because it's cheaper, but this is giving me a lot of constraints in terms of size and processing capability. And it's not anymore like the big satellites where I had huge batteries and huge solar panels. Here. I'm more limited in what I can do. But the good thing is that I have many of them. So I can have some distributed and cooperative solutions to have decent functionality and good performance. In terms of links, we can divide them in the ground to satellite link. So this is the link that connects everything that is on the Earth with a satellite. And it can be devices, so it can be a satellite phone, for example, and then we have a downlink and uplink, as we call them, or it can also be a link to the ground station where I have all the telemetry and maintenance operations of the satellite, and this is what it's called the feeder link as well. Okay, so this is to ground, but then in these constellations, I have a new kind of links, which is the direct communication between two satellites. And this is called the intersatellite link. And I can also divide them further and say that it can be the intraplane link when I just talk to a satellite that is in my same orbital plane. And this one is relatively easy because they are moving all together because they are in the same plane, no? So they move all together. But I could also think of talking to a satellite that is in another orbital plane, potentially even in a different altitude. So this means that the way we move is different, and this is more complicated for the communication and for the establishment of the link. Yeah, and here you have some examples of the rates that you can reach for each of these links. Okay, so for these LEO constellations, we have them three research problems, starting from the simplest case, in which the question is, which interplane satellites to connect to when I have several of them that I can reach, and how to do the resource allocation in this case. What happens here is that, I mean, in the same orbital plane, it's easier, no? I will typically talk to the guy that is in front of me and behind me. So this is easy. But with other orbital planes, depending on your topology, but there are a lot of situations in which you have several neighbors and you have to decide, okay, which one do you want to talk to now, no? And this turns to be a matching problem in which we basically decide which pairs of satellites will have a link, and everything is moving, so I have to change this decision all the time. So I have to move with the topology. No, I have to finish the previous link and establish a new link. Okay. To address this problem, we divide it in the two steps. So first we do the matching, where you have in the figure step one. No? This is about from all the feasible links, which we model as a graph, where the nodes are the satellites and the edges are the links, the communication links. I have to decide which pairs of satellites will talk to each other. No? And in the example of the figure, you have these thick lines that indicate that I do a match. Once I have the set of matches, I will do the resource allocation. And here we are talking about communication resources. In our case, it can be time frequency resources. So we have a limited amount of resources, time frequency resources, and we have to decide how to allocate them to all the links that we want to use. Of course, here we have also some interference, which we have to take into account to find the best allocation. Once I do this, the final output of this problem is to have the pairs of satellites that will establish the ISL, plus the resource that they could use in order to get the best transport capacity in the constellation. There are two possible approaches to this problem. The first one is the more theoretical one, but less practical, which is a centralized solution, in which we imagine that there is a centralized entity. It could be, I don't know, a geosatellite or a ground station that is doing all the calculations all the time. So it has to calculate the matching and the resources every t seconds because things are moving. So the decision has to change and evolve. But this, from a practical point of view, is very challenging because it means that you would need to receive a lot of information and to report a lot of information about the status of the buffers and the activation patterns to this central entity to take the best decision. So it's from a practical point of view is very difficult. So we have to think of a distributed solution instead, in which each satellite or each pair of satellites will decide to establish the link, and also will find a good choice of the resources to be used. To implement this distributed solution using some learning approach, the first observation is that it's interesting to use the predictability of the movement, because it's true that the topology is moving, so the graph is changing with time, but we know how things are moving because we know the law, the physical law that is giving us the next position of the constellation. So we can exploit this to make things a little bit easier. Still, the activity is unpredictable. We don't know exactly when we'll have packets to transmit and when the other guy doesn't have anything. So it's anyway challenging to implement these kind of solutions, but in principle, something based on learning automatas, where each action will affect the rest of actions is a good approach to find a distributed solution. The second problem, once we have the links that we can use, is okay, how to use them. So how do I find a path? Imagine I'm in Australia and I want to send a packet to Brazil. Of course, the satellite that is serving me in Australia is not covering Brazil because it's too far away. And these satellites at low orbits, the coverage area is small. So I need to forward this packet using the satellite constellation all the way to Brazil. And the question is, what's the best path or the best route to go from Australia to Brazil? So this is a routing problem, where in this case, we have this graph, which is the space segment of my constellation. And as you can see in the figure, you want to go from an Earth position somewhere to a final destination, which is a ground station in my figure. Routing has been studied a lot in terrestrial networks, but in satellite it becomes even more challenging. The first thing is that we want to have something that is reliable and resilient in our routing. And to have this, first of all, we should look at autonomous decisions, meaning that each satellite or each group of satellites should decide what's the best path. And this is different from the classical approach of having routing tables that are calculated on the Earth and then just sent to everybody. The problem here is that if you rely a lot on the ground link, the ground station and the link to ground, it's a problem because this link is limited and you also have to transmit many other information on this link. And also it's available only a few minutes and you don't have so many ground stations deployed on the Earth. So you have to be careful and you don't want to depend so much on the ground station. So solutions that are autonomous are very important here. So each satellite can find the best route. The other thing is the role of the feedback channel here. So feedback channel to send status information and to tell the other guy, okay, I received your packet, and this kind of information to help you improve your routing decision. So the role of this feedback channel is important, but of course it comes with a cost because it means additional complexity in the system. But these two are important for reliable and resilient solutions. Then we have this topology that is moving. To deal with this, as I mentioned before, it's important that in your routing you exploit the predictability of this movement. So each satellite in principle is able to predict how the constellation is moving. It knows where the other satellites are right now and what's going to be the next position. The other challenge is that if we have a general purpose system, in general, we want to support a variety of applications because we invested a lot of money on our system. So we want to have many different applications paying to use my network. And this means that we'll have heterogeneous users and requirements. So they will have a variety of, some of them, they want just the highest rate, others, they want a very low delay and very high reliability. How to put things together here, this has been studied also a lot in terrestrial, but quality of service aware routing, meaning that you give everyone what they want. You don't give the same to everybody, but is personalized. The last challenge is that we also have imbalanced load in our network. This happens also in terrestrial, but in satellite is even more, because think that some of the satellites, they will be covering the ocean and maybe there is nothing. So they receive zero traffic for a few minutes, but then they move and they are maybe covering New York, and all of a sudden they receive a lot of packets and so on. So the load is very imbalanced. And here it's very important to have a good traffic prediction. So based on learning or other methodology, but this will have a big impact in your routing decisions. Here I have some example of results where you can see for pretty simple routing algorithms with it's 3 different metrics, but the 3 of them, they are trying to find the best route considering the topology. So the hop count is just taking the number of hops that it takes to reach the destination. The path loss will also consider the total distance, and the latency will do an estimation of the total latency. So the latency metric in these examples is the most complex metric. And what we plot here is the total latency, end-to-end latency, And we show the different contributors to the latency. So we have the propagation time, that, remember, is the one that I cannot optimize. There is nothing I can do about this. I have the transmission time. And here there are also some theoretical bounds, but there is some optimization capability here. And the last one is the waiting time. This is related to the buffers and how I distribute my load. So here is where I can actually do a lot depending on which route I choose. And you can see it's just an example without going into the details of how the three components, they have a contribution in the total latency. And we have two figures because we have different values of the bandwidth. Okay, now I have a route between A and B. My final question is, okay, what's the end-to-end performance from A to B using this intersatellite link? In this figure, what you see is that now we have different sources and different destinations. So we have a light blue that goes from satellite 1 to satellite 3 here, and the dark blue goes from satellite 2 to satellite 4. And I want to know for all these end-to-end connections, what's the latency performance? You can observe in the figure that since there are other sources and other destinations, some of the links maybe I'm sharing with no one, and some other links, for example, from satellite 2 to satellite 3, I have to share my link with other connections, no? And this will change all the time because this is depending on how the traffic is moving. But this sharing of links is what we model with what we call the cross traffic in this multi-hop network to go from the source to the destination. What we use here is a queuing model to model this system, where we have that n nodes, each node is a satellite, and the last one represents the downlink to the final destination, to ground. On the arrival process on the left, we have the uplink. So from the Earth, source position on Earth to the serving satellite in the beginning, no? And then this satellite will forward to the next node and so on all the way to the destination. We had different versions and levels of complexity in this model, but okay, it's about how we model the random access in the uplink. Then for the communication links, we model cases also with errors. So some of the packets are lost. We also model the possibility of having priorities between different traffics and so on. So without going into the details, just to show you a little bit the trade-offs. Here is an example where there are errors in the link, and we have two metrics to measure this delay performance. We have the latency on the left, which is the classical metric, and then also this age of information that I mentioned. If we look at the latency on the left, it's the end-to-end latency, and we have different colors with increasing number of hops. So one is only you go up to the satellite and then down, and that's it. If you need to use a second satellite to forward, then it's 2 hops and so on. And then on the x-axis, rho, is the load of the system. Okay, so it's how loaded are your queues, and it depends on the arrival rate to the system. What you can see is that if you increase the number of hops, of course, your end-to-end latency is larger. And also, if you increase the load in the system, your latency will increase. And then you have also different line types to show the impact of the errors. And on the right, what you have is instead the age of information. And you can see that the behavior is different, because now what happens is that on the left part of the figure, when rho is very small, what's happening is that the frequency of the packets is not very large. So there are not many new packets created. So even though your network is quite idle, so it's not congested, you have room to put more packets in the system, but they are not arriving because in the generation process, the frequency is lower. What happens is that at the receiver, the edge of information is larger because of these not updates coming. On the right side is the opposite situation. They are very frequent, but the network is congested. So you arrive to a queue and you have to wait a lot because you have a lot of packets in front. So you have these waiting times in the queues, and the edge of information will also increase. In between, you have the optimal points in which the packets are frequent enough, but the network is not congested. So it's when the edge at the receiver gets the lower values. And you can also see the impact here of the errors, which is interesting because on one hand, you are losing some of these packets, but on the other hand, if you lose a packet in the first system, this will reduce the congestion to the upcoming system. So there is here a trade-off which is not trivial, but it's the impact of having multiple hops in the system here. Okay, so this brings me to the outlook. I talk a little bit about these non-terrestrial networks and what's the status in 3GPP and the standardization process. Then I focus on the LEO constellations, which is one of the systems that is attracting most of the attention, both from commercial missions and from research. And here the problem is that we have these links that are very dynamic, and we need some new and updated performance requirements to support these kind of networks. In terms of design principles, some of the observations, first of all, is, as I said, we want to reuse as much as possible what we know from terrestrial, but we need to do also some adaptations and some re-engineering, as we call it, to be sure that the terrestrial protocols, they can work also for satellite. The second thing is that it's very important here to look for distributed and autonomous solutions, because the satellites, they are not reachable, and we don't want to depend on the ground link too much. The predictability of the movement, I mentioned it several times. This is something that is interesting and is different from terrestrial, because in terrestrial things are moving more randomly. Here, I know how they are moving. And in general, we find a lot of problems in which we face untractable optimization. So there are many cases in which using learning approaches is interesting and can give interesting results. Okay, so this is all. I also have here some of the 3GPP documents, if anyone is interested. So I don't know if you have any questions.
Well, thanks a lot, Beatriz. This was a very, very interesting talk. I learned a lot of things, and I have some questions, but if first of all, if the audience has any questions, let's welcome them. Well, I can start as a warm up maybe. So the inter-satellite routing optimization problem is very interesting. My question is, at any time, how many other LEO satellites does a typical satellite see?
It depends a lot on the topology and the constellation, but if we take, for example, Iridium is a very regular topology. And in iridium, you always have 4 intersatellite links. So in the same orbital plane, it's always the guy in front and the guy behind. And then you have to the right and to the left. It's an easy topology because they are all deployed at the same height. The challenge is on the poles when they cross, but I think that they basically interrupt the connection in that area, because it becomes too difficult in the poles when everything gets close together, and yeah, it's more complicated. But in the rest of latitudes, it's basically 4 intersatellite links. This is iridium. I think in Starlink, it can even get larger than that number, but this is not very clear because Starlink has been changing many times the project and adapting, and of course some information is not really disclosed, but I think it can be even more.
So it's a mesh essentially. I mean, more so it's Starlink than Iridium. That it's a mesh that is moving, but you know, if you want to map this to a regular routing problem, we can think of the mesh as being static, but the users are moving. It's the same thing.
Yes.
So this is, I mean, brings all kinds of questions actually. One of them being, you know, if you have a queue where you're serving multiple flows, what kind of service policy? I mean, do you want to just prioritize some flows that soon will be, you will be moving out of the coverage of, or etc. You could do various things. I guess minimizing the number of satellite to satellite handovers should be one of the goals. I mean, this is very interesting.
Yeah, we also want to minimize also the interplane, which is more expensive and more limited. The intraplane, okay, it's stable.
Right.
Yeah.
But the interplane, you just use to transmit actual data.
It's open. It goes from mission to mission. But yes,
I see.
That's probably the best you can do, and keep all the reliable and control information as much as possible within the same orbital plane.
I see. Do you think we could make a semantic communication use case?
Absolutely.
That involves this. I mean, I'm asking pretty much for the benefit of our paper. It's so.
Absolutely, yeah. In this multi-hop setup, we found a lot of interesting trade-offs, and we still don't have the mobility because we had to start with the simplest. So we just take a snapshot, and so it's not moving, and we do the study, and then next time it will be in another position. But I think if you add the mobility and then the routing there and add the semantic, then it's a lot of interesting trade-offs, yes.
So perhaps I can take a look at your paper to get some, I mean, if we could find 1 or 2 interesting curves that shows that treating regular performance metrics and treating semantic measures is different, requires different handling of this routing and scheduling problem, that would be very interesting, I think. Okay, any other questions from the audience? Okay, one more question from me. How close, so basically I see there are some requirement documents.
Sorry?
I see some requirement documents like on this page.
Yes.
So will any of these make it to 5 5G. I guess they are making it partially to 5G.
Yeah, to release 17 and release 18, it's not super clear now, but I think release 17, yes, at least the latency that I mentioned, this adaptation to the satellite, yeah, it will be in release 17.
Mm-hmm.
But you know, they have been changing plans because there was a little bit of revolution in 3GPP with the pandemic because they cannot meet anymore. So they had to change all the procedures, and there was at least 6 months delay. And now they are also, some of them are pushing and they don't want to prioritize satellite. So maybe it will be very limited what we see in release 17, and everything will be to release 18 and 6G point.
Yeah. I'm also interested in the connection between, you made a point about whether there's random access or not, the problem changes. Do you have a paper that deals with this?
Yes, we do. I will share with you. So we model Aloha on the uplink. Yeah, so just to shape the arrival rate to the queuing network after that. I will share with you.
Yes, that would be great. Thank you.
Yes.
Well, if there are there any other questions, everyone? Don't hesitate. Okay. Well, maybe we should take more of your time, Beatriz. Thank you so much for visiting us.
Thank you very much.
Let's be in touch. I'm looking forward to looking at your paper.
Yes.
And I hope we can get to meet again soon.
Yeah, me too. Okay, thank you very much.
Bye-bye.